Hi, so welcome to the midterm review. What I'm going to be doing in this video is really walking us through all of the different concepts you need to feel pretty confident with in order to ace the midterm. So I recommend watching this before you start actually studying, because I'm not going to be going through much in a huge amount of depth. I'm really aiming to just be comprehensive and to give a really brief but still, fairly in some depth overview of everything that you need to know in order to get 100% on the midterm, which is totally within reach of everybody. So I'm thinking of the midterm as really being divided into 4 different sections. So here's the first section, and it will form the first part of the roadmap for this video. Okay, the first section is really dedicated to arguments, practical and factual arguments, inductive and deductive arguments, soundness and validity, and strength and cogency. I'll be walking us through each of those 4 different things shortly. The second section is all about informal fallacies. The next is really about translating arguments or sentences that are written in English in natural language into symbolic notation. And then the final sort of group of topics is all about truth tables. So we'll look at truth functions and truth tables, then we'll look at tautologies, contradictions, and contingent sentences, and how we can use truth tables to figure out of any individual sentence whether it's a tautology, contradiction, or contingent sentence. And then we'll be using truth tables to determine whether an individual argument is valid or not. So that's the roadmap. And I've highlighted the different sections in colors because, at least to me, those colors sort of group the topics by theme. So let's start with the first of the first group. We're going to talk about arguments, and we're going to start by looking at this distinction between practical and factual arguments. First up though, super basic point, arguments are sets of sentences. I should say arguments are sets of sentences. Let's make that. Okay, so a single assertion like the one I have here, dogs are the best, isn't an argument. Okay, super basic point. As we understand arguments in logic anyway, okay, arguments are sets of sentences. So we're using a kind of technical definition of arguments here. Okay, so another key technical term is the term premise. One or more sentences in this set that I'm calling the argument, one or more of those sentences are going to function as premises. And another of those sentences is going to be the conclusion. And the idea is that the premises support or give us reason to believe the conclusion. So everything that I've said on this slide is true of every single argument you can think of. I'm going to be talking about a couple of different distinctions between practical and factual, and then inductive and deductive arguments. Okay, but whatever argument we're thinking of or you're thinking of, it's always true that an argument in logic is a set of sentences. Okay, so a single assertion is not an argument. It's always true that one or more of the sentences in that set function as premises, and it's always true that the premises are supposed to support the conclusion. All right, so let's just talk about one of the most basic distinctions, and that's between practical and factual arguments. Okay, so how do we know when an argument is a practical argument? Well, the conclusion is a statement of what someone ought to do or should do. Okay, so we know that an argument is a practical argument when its conclusion is a sentence like you should make a sandwich, or Mary should go to school, or one ought to eat breakfast every day. Okay, if you have a conclusion like that, That's a prime indication that the argument is a practical argument. Okay, so what's going on with a factual argument? Well, the conclusion of a factual argument is a statement about how the world is or what will happen. Okay, so it's a claim that purports to be a statement of fact, like, for instance, grass is green, or pigs can fly. Even that one, pigs can fly, it's kind of absurd. It's not the case that pigs can fly, but it's a sentence that's purporting to be about the world. When I say pigs can fly, I'm purporting to make a statement of fact, to describe how the world is. I'm wrong, but I'm still in the business of describing the world. I'm not making a statement about what someone ought to do or should do. And so my argument is a factual argument. Okay. Let's talk about the next distinction between inductive and deductive arguments. Now, both factual and practical arguments come in these two different varieties, inductive and deductive. How do we know whether an argument is inductive? Well, the conclusion goes beyond what the premises state. Okay, even though the premises, because they're premises, are supposed to make it reasonable to believe the conclusion. Okay, they're supposed to support the conclusion. But what the premises are doing is providing evidential support, not definitive proof. Okay, I'm just going to contrast this with deductive arguments now, and then we'll look at some examples. So with a deductive argument, the conclusion is supposed to be entailed by or to follow from the premises. And so here, the premises are meant to provide conclusive or indisputable reasons to accept the conclusion. And that's quite different from what's going on with inductive arguments. In inductive arguments, the premises are not supposed to make it indisputable that the conclusion is true. They're supposed to make it reasonable to believe the conclusion, but they're not in the business of providing that kind of conclusive, definitive proof. Now, I've made this slide not because it's super important for people to think much about this, but just because I'm sure people will be thinking about how this distinction between inductive and deductive arguments hooks up with that distinction I drew at the very beginning between practical and factual. So I just want to say here that these distinctions are orthogonal to one another, meaning that, okay, you can draw up this graph if you really want, okay, and you could fill in each of these, what's this called? Each of these cells, okay? So you can have an argument that's practical and inductive. You can have an argument that's factual and inductive, or factual and deductive, or deductive and practical. So these are just two different sets of distinctions. They're orthogonal to one another, but it's important for you to have a really sort of basic grasp on how to identify a practical argument, how to identify a factual argument, and how to distinguish between inductive and deductive arguments. Having said that, for the most part, we're going to be interested in factual arguments in this course as opposed to practical ones. Okay, so understand the distinction between those, but then at the same time, you can kind of leave that behind and just know that we're going to be focusing on factual arguments for the most part of this course. Okay, so the examples of inductive and deductive arguments that I'm going to give us are examples of factual inductive and deductive arguments. Okay, so here's an example. And I want you to think about whether this is inductive or deductive. Premise 1, the subway has been late every morning this week. The conclusion is therefore the subway will be late again today. If you're asked, is this inductive or deductive? You have to think to yourself, okay, is the premise trying to make it indisputable that the conclusion is true? Or is it functioning sort of to provide evidence for the conclusion, to make it pretty reasonable to believe that the subway will be late again today, but you're not being sort of illogical if you don't agree that the subway will be definitely late today? So if you ask yourself that question, I hope you sort of agree that this argument is inductive. The subway could be true rather that the subway has been late every morning this week. But that doesn't necessitate that the subway will be late again today. It's possible that today will just be different. Who knows? It's always possible. It might be super reasonable to expect it to be late, but it's not impossible for it to be on time today. And because it's not impossible for it to be on time today, the argument is inductive. What about this one? If the subway's late, then I'll be late for work. Premise 2, the subway is late. The conclusion, I'll be late for work. Do these premises make it just pretty reasonable to believe that the conclusion is true? Or do they entail the conclusion? Do they necessitate the truth of the conclusion? I hope everyone will agree that this one is deductive. If you believe premises 1 and 2, you'll be committed to believing that, yeah, you're going to be late for work today. These premises aren't just making it reasonable to believe the conclusion. They're not just providing evidential support. They're in the business of providing definitive proof for the truth of the conclusion. If you believe the first 2 premises, you really ought to believe the conclusion. Okay, so that's all I'm really going to say about these 2 different distinctions between inductive and deductive and factual and practical. Here's one way of sort of making sense of what we've done so far. We've got arguments up here. Arguments can be factual or practical. Practical arguments can be inductive and deductive, right? There's nothing I've said says that they can't be, okay? But we're going to be mainly interested in factual arguments here. So it's important to recognize that factual arguments can come in deductive and in inductive varieties. Okay, so from now on, we're just going to be focusing really on, I want to isolate, we're going to be looking at this branch of the tree, okay, the factual branch of the tree. All right, the next pair of concepts you need to 100% have down is soundness and validity. Now, these are 2 different properties that deductive arguments can have. So when we talk about soundness and validity, we'd better be talking about a deductive argument. Okay, hopefully this is all just sounding super familiar. What's validity? Well, an argument's valid when the truth of the premises necessitates or entails the truth of the conclusion. And I'll come back to explaining more about what's in parentheses here, but an argument can be valid even if the premises are in fact false. All that we're interested in when we're thinking about the validity of an argument is its form, is whether the premises necessitate or entail the truth of the conclusion. Another way of putting that is whether it's the case that if the premises were true, they would make it impossible for the conclusion to be false. Okay, whether they necessitate the truth of the conclusion. So an argument can be valid, and that's a good thing, but an argument can also be sound. If it's sound, then it's valid and the premises are true. So a good deductive argument is valid, but an even better one will be sound. All right, then let's look at some examples. Premise 1, if grass is green, pigs can fly. Premise 2, grass is green. The conclusion is pigs can fly. Is this a valid argument? Yep, but it's not sound. Why is it not sound? Well, if grass is green, it's not the case that pigs can fly. So premise 1 is false. But that doesn't matter because the argument is still valid. So it's not a terrible argument. In terms of logical form, it's pretty good. It's valid. So this kind of example makes that really clear, but it's worth just saying that a valid argument can have a false conclusion. Super important to remember that. So in fact, I might just italicize it. a valid argument can have a false conclusion. How do we know if an argument is valid? Now, I've already sort of said this, but let's just write it up so it's super clear. You ask yourself this question. If the premises were all true, would the conclusion have to be true too? Okay, so you say, let's just imagine a world in which the premises were all true. Would it be the case in this world that the conclusion would have to be true? If the answer to that question is yes, then the argument is valid. If the answer is no, then it's invalid. So going back here, we ask ourselves of this argument, in a world in which premise 1 and 2 is true, in a world in which it's true that, well, if grass is green, pigs can fly, and in a world in which grass is in fact green, is it necessary that pigs can fly? And the answer is yes. If the premises are both true, the conclusion has to be true. Okay. So now let's talk about strength and cogency. And this is a pair of concepts that apply to inductive arguments. Just as validity and soundness are two properties that deductive arguments can have, strength and cogency are two properties that inductive arguments can have, and they are two ways we can kind of measure the goodness of an inductive argument. Two ways we can assess whether an inductive argument is a good one. So first we have strength. And an inductive argument is strong if the premises provide strong evidence for the conclusion, or they make the conclusion highly probable. So unlike validity, okay, where if an argument is valid, the premises necessitate the conclusion. If an inductive argument is strong, then the premises just make the conclusion highly probable. Could be false, but it's highly probable that it's true. What about cogency? Well, as soundness is just validity plus two premises, cogency here is strength plus two premises. So there's a real kind of parallelism between strength and cogency for inductive arguments, and validity and soundness for deductive arguments. So let's look at some examples. Premise 1, the bus has been late every day this month. Conclusion, the bus is going to be late again today. It's an inductive argument for sure. Is it strong? Seems to me to be pretty strong. Every day this month, that's a large amount of evidence, right? The fact that the bus has been late every day this month, okay, premise 1 isn't just talking about what's been true yesterday or the last few days or even this week. Premise 1 says it's been late every single day this month. So that's a lot of evidence, right? It makes it highly probable that the bus is going to be late again today. So it's strong. But is it cogent? Well, it's hard to know. It depends on whether P1 is actually true. You need to, in order to know whether this argument is also cogent, you need to figure out whether premise 1 is in fact true. And I've just made that up, so I'm going to tell you it's not true in this case. Here's another one. Every dog I've met has had canine teeth. Conclusion, all dogs have canine teeth. Again, that's a pretty strong argument, and I'm going to tell you it is cogent because premise 1 is true. Every dog I've met has had canine teeth, as far as I know. So this argument is strong and cogent. But note that the conclusion could still be false. It's not impossible for me to come across a dog that doesn't have canine teeth, okay? Maybe it's lost all of its teeth. Maybe it just had a genetic anomaly or something and doesn't have canine teeth. Okay, so here's a really important contrast with deductive arguments. Here we have on this slide up here, the thing I'm highlighting now, we have a cogent inductive argument. So it's like the best kind of inductive argument we can have. Unlike its equivalent deductive argument, a sound deductive argument. Remember, sound arguments are the best kind of deductive arguments. Unlike that kind of deductive argument, the conclusion of a cogent inductive argument could still be false. Okay, it's possible that this conclusion is false, but the conclusion of a sound deductive argument is always going to be true. So that's a really important difference between inductive and deductive arguments. The best kind of deductive argument, a sound one, will always have a true conclusion. That's not true of the best kind of inductive argument. Okay, some final points to make about everything we've said so far. Inductive arguments can't be valid or invalid or sound or unsound because the concepts of validity and soundness do not apply to inductive arguments. That's really, I've already made that point, but I just thought it's worth reiterating it. You can't say of an inductive argument that it's valid or it's sound. It just doesn't make sense. Similarly, deductive arguments can't be strong or weak or cogent and not cogent. Those concepts, strength and cogency, just don't apply to deductive arguments. Okay, final kind of final kind of point I just want to make so everyone's got it really clear in their head. It's not quite right to describe arguments as being true. Remember, arguments are sets of sentences. Individual sentences, like premises or a conclusion, those can be true. But when we're describing the quality of an argument, we use the concepts of validity and soundness when we're talking about deductive arguments, and strength and cogency when we're talking about inductive arguments. And I've put this point on the slide just because often in the first part of this course, people tend to say this argument is true or this argument is not true. And technically, that doesn't really make sense. You can say that this argument is valid or sound or strong or cogent, and you can say that this premise is true or false, and this conclusion is true or false. But an argument is a set of sentences, and we have other concepts to assess the goodness or to assess the quality of arguments. Those are validity and soundness and strength and cogency. All right, next sort of section, we're just going to talk about one bundle of things here, informal fallacies. Now, I've just decided to put all of the informal fallacies that appear in the textbook on this slide. They come up in chapter 3. If you're looking at the manifold version of the textbook, it's chapter 3. In some versions, it's chapter 1.3, meaning unit 1, chapter 3. But basically, here are all of the informal fallacies that make an appearance there. An informal fallacy is a pattern of reasoning that's actually a bad pattern of reasoning. It's not good to commit an informal fallacy, but it's a super, super common mistake. And so because these mistakes are so common, they've been given these names, like for instance, the appeal to authority or a straw man or a slippery slope. Now, I'm not going to go through each of these informal fallacies. I'm going to leave it to you all to go to the textbook, look at your notes, and do your revision there, because different instructors will have different preferences about which informal fallacies are the most important ones for you to focus on. So I'm just listing the names of them here and letting you know that you can look at chapter 3 to revise for this section. Okay, next, we're going to talk about translations. So far, when I've been putting arguments in standard form, so when I've been writing premise 1, premise 2, C for conclusion, when I've been presenting arguments in the slides, I've been using English language. I've been writing sentences like, if grass is green, pigs can fly. But it's going to be helpful if we can translate those sentences from English into something more formal. And so that's what we're doing when we're translating arguments into symbolic logic notation. Okay, just said that part. Here are the basic components of the language that is symbolic logic. Okay, now these are called logical operators. Each of these logical operators has a different meaning. So different English language sentences take different logical operators when they're being translated. Here is how you translate the logical operator into natural language, in this case English. So this symbol, we say and, it means and, but its technical name is the conjunction. Here we have this symbol. In English we say it's or, but its technical name is the disjunction. Negation, conditional, and biconditional. Okay, that should all be super familiar. These are the basic building blocks or components of symbolic logic notation. But we can't use these logical operators on their own. They're used in conjunction with atomic sentences. So what have I said here? Logical operators, they connect atomic sentences. So an atomic sentence is something like the sentence, Bill is a dog. And those atomic sentences are represented when we're using symbolic logic notation by variables like P, Q, R, and S. So our basic sentences, the most atomic kinds of sentences we can find. Okay, Bill is a dog is an atomic sentence because we can't break it up into any smaller component parts. We represent this sort of atomic sentence with a variable like P or Q or R or S. And then we join those atomic sentences with other atomic sentences via logical operators to make ever more complex sentences. Like, for instance, Bill is a dog, or Bill is a cat, okay? We might, if we have this, we have Bill is a dog, or Bill is a cat, okay? We can translate that with P or Q, where P stands for Bill is a dog, and Q stands for Bill is a cat, okay? That should be fairly, nothing new there. Here's an important point though that is worth reiterating as everyone's preparing for the midterm. Actually, two important points. The first is just the conditional. I'm sure everybody's memorized this point so far, okay? There are many different ways we can express the relationship that the conditional logical operator represents. There are many different ways we can express that when we're using natural language, okay? So here's one. If we say something like, if P, then Q, that translates to P arrow Q. If we say Q, if P, that translates in exactly the same way. Okay, Q if P is exactly the same sentence as if P, then Q. And then we have one more, Q unless P, that translates into if not P, then Q. And so it's just important to sort of have these three different varieties in your mind, and you feel confident translating each side to the other. Next super important point is about ensuring that your sentences are well formed. What does it mean for a sentence to be well formed? Well, it means that there's no ambiguity about how to understand it. So here's an example of a sentence that's not well formed. I'll just highlight it here so it's super clear. this sentence is not well formed. It's not clear, right, whether it means this, okay? Let me highlight that in green, or whether it means this, and I'll highlight this one in green. Okay, so does it mean if P then Q or G? Or does the sentence mean if P then Q or G? Those are two different sentences, the things that are highlighted in green, and it's not clear whether the thing that's highlighted in yellow means the one on the left or the one on the right. So it's not well formed. And here's another example. We have P and Q or G. It's not clear whether this sentence means P and Q or G, or whether it means P and Q or G. So what I think these examples make clear is that in order for a sentence to be well formed, it needs to have brackets in the places where brackets are needed. Okay, here, this sentence that's highlighted in green is missing a pair of brackets. And the same is true of the one on the top. How do we know how many pairs of brackets? Well, here's a nice sort of pithy way of just remembering it. A sentence is going to be well formed when there's one logical operator, except for negations, that isn't in parentheses. So let's go back to the last slide. Here, what I'm highlighting with my cursor on this slide, these two sentences are well formed because there's only one logical operator. On the left hand, in the left-hand sentence, it's the or, the disjunction. The right-hand sentence, it's the conditional, the arrow. Each of those sentences has only one logical operator that's not in brackets. And when that's the case, it's super clear what the main logical operator is. So here, the main logical operator is a conditional because the arrow is the operator that's not in brackets. And that means this sentence is basically just a complicated conditional sentence. It says, if P is true, then this disjunction is true. On the other hand, this sentence, the main operator is the or, the disjunction, and that means this sentence is basically just an or sentence. It's a complicated or sentence, but nonetheless, it's just a disjunction. It's just the case that the left-hand disjunct, the thing that's on the left of the arrow, this bit, is itself not an atomic sentence, it's a conditional sentence. But the sentence as a whole is just a disjunction. Okay, so that's how you can tell whether your sentences are well formed. There's only one logical operator, taking exception to the negation, that isn't in brackets or parentheses. Okay, now we're going to talk about truth functions for logical operators and truth tables. Okay, so first thing to note is that a complex sentence, a sentence that has a logical operator in it, not a sentence like P or Q, okay, those are atomic sentences. A complex sentence is going to be true or false depending on the combination of truth or falsity of the atomic sentences that are its parts. Okay, so we can think, this is just sort of another way of spelling out what I've just said. We can think of the logical operators as functions, and they take the truth or falsity of the atomic sentences as inputs, and they have either truth or false as outputs. Okay, we need an example, I think, to make this a little bit more concrete. Here's an example. The sentence P and Q. It's a complex sentence. Why? Because it has atomic sentences that are its parts. This sentence, P and Q, will be true whenever P is true and Q is also true. If either P or Q is false, then the complex sentence is itself false. So we can think of the function and it's going to give us true for this sentence. This sentence, P and Q, will itself be true whenever both of its component parts, the P and the Q, are true. If either part is false, then the complex sentence is itself going to be false. All right. What I've just said will hopefully make sense just intuitively, right? But we're able to represent it by drawing up a table for each of the logical operators, each of the and, or, the conditional, the negation. And this table is going to show all the different possibilities of atomic sentence truth values and indicate what that means for the truth value of the complex sentence itself. So we're going to draw up a table. The table is going to represent all of the different possible combinations of P's truth or falsity and Q's truth or falsity. And the table is also going to indicate the consequence of that for the truth value of the complex sentence itself. In this case, P and Q. All right. Now I'm going to give us more examples to make that all more concrete. But just to say, the content of the following slides is something that you need to know off by heart. Not just to ace the midterm, but to be in a position to ace everything that comes after the midterm too. So this knowledge is going to be required for the rest of the semester. So it's super, super, super important that you understand everything that I'm going to say and you have these tables memorized. So we're going to draw up a table for each of the logical operators. Okay, so here's the table for the disjunction, P or Q. We have in the very left column, we have the possible truth values for P. We have true, true, false, and false. Then we have the possible truth values for Q, truth, false, true, false. And for each of the rows, so let's look at row 1 first, we're going to indicate in the final column whether the sentence P or Q is itself going to be true. Okay, so on row 1, we have P is true and Q is true. So on that row, the disjunction of P and Q is itself going to be true. So we write T there. On the second row, we have P is true, Q is false. So the disjunction of P and Q is itself going to be true. Here we have false and we have true. The disjunction is still going to be true. Here though we have false and false. And when P is false and Q is also false, the disjunction of them both is going to be false. Okay. Why? Because for a disjunction to be true, at least one of the disjuncts, the things that it brings together on either side of the V, at least one of those things has to be true. We don't have that on the fourth row, and so the disjunction is going to be false. Okay. So 2 things are just worth making super clear. Each row shows us a different combination of truth or false for P and Q. So we have 4 rows in our truth table in total because we have 2 different variables, and each variable can take 2 possible truth values, either true or false. And so all up, there are going to be 4 different possible combinations of truth values. So each row shows us a different combination, and the table as a whole shows all possible combinations. Okay, so I've made those 2 points. These 2 points are important to remember whenever we're looking at a truth table, just in case you sort of forget what's actually going on. Why are we doing this? What does it represent? What's it supposed to be showing me? All right, the conjunction. I filled this one out for us, okay? We look at P and Q. P and Q is going to be true whenever both of the component parts, both of the conjuncts, P in this case and Q in this case, both of the conjuncts are true. That only happens on line 1. So the truth table for the conjunction is going to have true here and false everywhere else, because on each other row, we have at least one false. The conditional, okay, has true when both P and Q are true, and it has false here. It only has false once. So this table is showing us, hey, the conditional sentence is true all of the time, except for when the antecedent, the thing that comes before the arrow, the thing that comes to the left of the arrow, except for when that's true, and the thing that comes after is false. When we have a true antecedent and a false consequent, the conditional is going to be false. At any other time, it's going to be true, okay? Here we have true, and here we have true. Now, you might have had at some point in the semester a bit of confusion about why we fill out the truth table for the condition like this. Basically, the important point to know is that this sentence, if P then Q, we know that this sentence is going to be false whenever P is true but Q is not true. Right? Why? Because this sentence is saying, the meaning of the sentence is, if P is true, then Q is going to be true as well. That's exactly what this means. So if it turns out that, in fact, whenever P is true, Q isn't true, right, then that sentence is going to be false. So if you look out into the world and you find an instance where P is true and Q is not true, then you know that if someone tells you, hey, if P then Q, you know that they're saying something false. And because that's all we can really say about a conditional, we can say that it's false whenever the antecedent is true and the consequent is false. We fill out the truth table this way, with true everywhere except for on that line where we have a false antecedent, a true antecedent and a false consequent. Okay, the negation, super simple. Whenever P is true, not P is false. Whenever P is false, not P is true. That is the most simple. And the biconditional. A biconditional, remember we say P if and only if Q. That's how we sort of translate the biconditional into natural language. The biconditional is going to be true whenever the two things that it brings together, in this case Q and P, whenever those two things have exactly the same truth value. So on the first row, the biconditional is true, and on the last row, the biconditional is true because P is false and Q is false. So they have the same truth value. All right. That was truth functions for logical operators and truth tables. You need to make sure you have all of those tables sort of down in your brain. You feel totally confident. You see why we fill them out that way, and you're able to sort of recall the way we fill them out whenever you need to. Now we're going to start talking about why these truth tables might be helpful at all. Okay, so we're in a position now to construct truth tables for more complex sentences. Okay, so here's an example of a pretty complex sentence. The main logical operator is an or, okay, and it's made up of a conjunction and a conditional sentence. So you might get presented with a table like this, a truth table like this one here in an exam, and you'd be asked to fill it out, okay? Fill out the truth table for this sentence. So what that means is you'd be presented with the true, false, false, true, false, true, false on the very left-hand side. And then you have to fill out the rest of it column by column. So you start with the column that's most to the left, in this case, the conjunction of P and Q, and you fill it out using those skills that you should have by now. Those skills of knowing how to fill out the truth table for each of the logical operators, because we're just going to be doing this one step at a time. So the first step is just filling out the truth table for the conjunction of P and Q, so we know how to do that. We have it will be true here, it will be false here, false and false. Now we have not P. Okay, well, P is true, not P is false. P is true, not P is false. P is false, not P is true. P is false again, not P is true. Now we're going to have the conditional with not P being the antecedent. So this row that I'm highlighting here is the antecedent. And this row here, Q, is the consequent. So I'm going to look for any row which shows me that I have a true antecedent and a false consequent. I have that row here. On the fourth row, I have not P comes out as true and Q comes out as false. So at the fourth row, I know that the conditional is false. At every other row, it's going to be true though. And now I have a disjunction in the final column of what? Of the conjunction, which comes up over here, this row, and the conditional that comes up here, this row. So now I'm looking at those two columns that I just highlighted, and I'm filling out the truth value for this sentence based on the truth values of those two columns. So here, row 1, I have true, true. So this junction is going to be true. Here I have false, true. That's going to be true. False, true, true, false, false, false. Okay. So we've filled out a truth table for this sentence. Why is that a useful thing to do? Well, now we're in a position to say something about this sentence, okay? What the truth table represents, it shows us in this final column, it shows us exactly when this sentence is true and when exactly it's false. There are 4 different possibilities, 4 different possible combinations of the truth and falsity of the atomic sentences that are its parts. 4 different combinations, hence 4 different rows. And it's true all the time except for what's happening on this final row. So it's true all of the time except for when P is false and Q is false. If both P and Q are false, then this sentence as a whole is also going to be false. At any other time though, it's going to be true. Okay, so why is this helpful? Well, we can use a truth table to determine whether an individual sentence is a contradiction or tautology or a contingent sentence. So I'm going to tell you again what these 2 sorts of sentences are. And this is something you just need to another thing you need to remember, not just for the midterm, but for everything that's going to come after the midterm as well. So a contradiction is a sentence that is never true. It is logically impossible for a contradiction to be true. So here's an example. Snow is white and snow is not white. This is a sentence that is just impossible for it to be true. Okay, snow is white and snow is not white. That's a contradiction. It can never be true. What about a tautology? Well, a tautology is a sentence that's always true. So here it's logically impossible for it to be false. Snow is white or snow is not white. That's an example. It's always going to be true that this sentence, it's always going to be the case that this sentence is true. It's impossible for this sentence to be false. And then we have a final category of sentences, and these are just contingent sentences. Sentences that can be true or false. There's nothing about their logical structure that means that they need to be true or false all the time. They're just sentences that depend on the truth or falsity of their parts. There's nothing about the form that means it's impossible for it to be true or it's impossible for it to be false. Okay. So an example is snow is white and I'm hungry. Whether that's true or not is going to depend on whether indeed snow is white and whether indeed I am actually hungry. There's nothing about the form of the sentence that indicates whether it's always going to be true or always going to be false. Okay, so now let's look at the truth table for the sentence we just filled out. And we're going to ask ourselves whether this sentence is a contradiction, tautology, or contingent sentence. And we do that by looking at the truth values that come up underneath it. So we look at the column that represents the truth value for the sentence. And we look, okay, is it always true or is it always false? Or is it sometimes true and sometimes false? Here we have an example that says where it's sometimes true and in one situation it's false. So it's neither a contradiction nor a tautology. It's not impossible for it to be false. Look, we have falsity on the final row. But it's also not impossible for it to be true because we have 3 rows at which it's true. So it's not a contradiction and it's not a tautology, so it's definitely a contingent sentence. Okay. If we looked at this final row and we just saw true, 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 then we could say that the sentence is a tautology. It's impossible for it to be false. If we saw here false, 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 then we'd say it was a contradiction. All right. Final section, we're going to show how we can use truth tables to determine whether an argument is valid. And this is sort of the most awesome thing about truth tables. The coolest thing we can do with them, or the most useful thing we can do with them. Okay, so we can, in addition to determining whether a sentence is a tautology, contradiction, or contingency, we can determine whether an argument, which is a set of sentences, is valid or not. And just a reminder, an argument is valid if, whenever the premises are all true, the conclusion must be true. All right. So I just said those first 2 sentences. What we're going to do is we're going to use a truth table to represent all of the premises and the conclusion. So we're going to have at least 2 different sentences that are going to be represented in our truth table. And then we're going to see whether the conclusion is true whenever all the premises are true. So I'm going to run through one example just to make that more concrete. Here's an argument, 2 premises, 1 conclusion. Now, if I'm going to be building a truth table for this argument, then I'm going to have 3 different sentences represented in my truth table. So here's what that looks like. All right. Premise 1, the disjunction of P and Q, that's going to show up first. I'm going to put that up here. And I fill out the truth table for that. I've got true, true, false, true, 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 false. Okay. Then I do not P. So I'm in a position to do not P. If not P, then Q. I have true, 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 false there. And then I have a column for my conclusion, the conjunction of P and Q. And I have true, false, false, false. So I fill this out. I have a truth table that shows me every possible combination of truth and falsity of P and Q, what that means for the truth and falsity of my premises. Here is highlighted in yellow every row at which premise 1 is true. At this column, highlighted in yellow, I have all the rows at which premise 2 is true. And so once I have gotten that, I say to myself, okay, let's look at all of the rows at which all of the premises are true. Okay, so here, if a row 1 is one instance where both of my premises are true, and then I look there whether the conclusion is true. So here I have a row at which premise 1 is true, premise 2 is true, and the conclusion is true. Okay, so that's good. What about though row 2 and row 3? On row 2, I have premise 1 is true, premise 2 is true, but my conclusion is false. So on row 2, I found a situation where I have true premises and a false conclusion. So on row 2, I found a situation where the premises are true, but the conclusion is false. And so this is a counterexample to the argument. This is enough, row 2, independently of what's going on in row 3. I have shown already at row 2 that the argument is not valid because I've shown that it's possible for the premises to be true and the conclusion to be false. So whether or not whatever's going on row 3 is actually unimportant because I've already found one row at which I have true premises and a false conclusion, and that's sufficient for me to show that the argument is not valid. If the argument was valid, I would have truth in the conclusion row every time I have truth in all of my premises. Okay, so if this argument was valid, this is what the truth table would look like. I would have, hey, true premises at rows 1, 2, and 3. And at each of those rows, I have a true conclusion. But in fact, this is what it was like. So we can say, definitely not valid. Okay, now let's go back to the roadmap. So we've done determining validity using truth tables, and that's the final section. Now, just to remind you all what we've done, the first bunch of concepts is really just about understanding different kinds of arguments and understanding the concepts we use to assess different kinds of arguments. Then we've got the informal fallacies section, and then we've got translating into symbolic notation, and that's the first step towards building truth tables and using truth tables to determine what kind of sentence we have, tautology, contradiction, or contingency, and then also whether we have a valid or invalid argument. And if you feel good about everything that's on this roadmap, then you're totally set to get 100% on the midterm.